Okay, so hi. I'm Alessandro Chiesa, so I'm a faculty member at UC Berkeley. I work in cryptography and complexity theory. I'm also a chief scientist at Starkware, was also a co-founder of Zcash. And today I would like to tell you a little about recent work that we had in the area of cryptographic proof systems. This is joint work with Eli, who just gave the previous talk, Mikhail Ryabtsev, who is also at Starkware, Nicholas Spooner at UC Berkeley, Marius Virza at MIT, and Nicholas Ward also at UC Berkeley. So while in the prior talk we mostly focused on scalability, the talk that I will give right now is more focused on achieving privacy by way of cryptographic proofs. Okay, so the title of the talk is Aurora. Okay, and that's the name of the system that we built. And I will tell you about how to build transparent, succinct arguments for the language R1CS. Okay, if you're interested to look at the paper, it's available online at the link below. All right, so this talk is about ZK SNARKs. So let me spend just one slide to remind you what ZK SNARKs are. So they are a type of cryptographic proof system that enables you to produce non-interactive written down proofs for computational statements of integrity. So for example, a statement such as, I know a secret W such that Y is the correct output of the function F applied to the secret W. Okay? Now, why are these proofs special? Because they have certain privacy and efficiency properties. The privacy property is called zero knowledge, okay? In this case, the proof itself provably hides information about the secret W. The efficiency properties of SNARKs have to do with the size of the proof. So essentially, what we call succinctness, which dictates that the size of the proof only grows polylogarithmically in the length of the computation that is being produced. Okay, this is kind of analogous to how earlier you saw this exponential gap between sort of the size of the computation and the size of the proof that attests to that computation. Okay. Now, in the previous talk, we also focused on the succinctness of the verifier. Okay, this means that not only the proof is small, but also the process of verifying the proof is fast, exponentially faster than the computation it attests to. Today, it will not be a focus because it will not be something that we achieve. We'll be mostly focusing on small proofs. Now, over the past few years, there have been many beautiful and efficient constructions of ZK SNARKs. We've also seen real-world deployments, such as in Zcash, and there are sort of more deployments that we'll see, I'm sure, this year, for example, through scalability applications for DEXs. The focus of our work was to study a particular class of ZK SNARKs that are so-called transparent. Okay? These are those that do not rely on any trapdoors in the setup. Okay? So you can think about the only public parameters of the system are sort of pure public randomness. Okay? I will not focus too much on what trusted setup here means. I think there are, at this point, enough online resources to learn about that. Okay? But our focus is on transparent SNARKs. So how do you construct ZK SNARKs? So most constructions have two parts. One is, you can think about it as a front end. It's a reduction that takes a problem that you care about, for example, a statement about the computation, and reduces it to some intermediate representation that usually involves some statements about algebra. Okay? In a subsequent step, you have a proof system that picks up this intermediate representation and actually produce some proof string that attests that some properties about this sort of intermediate representation holds. Because of this two-step process, the choice of intermediate representation is very important because it affects both the efficiency of the reduction and the efficiency of the proof system. Okay? And today, we'll discuss, I'll tell you a little bit about a proof system for an intermediate representation that has shown strong empirical value in practice. In fact, we already had a talk about this intermediate representation this morning, okay? And the language is that of rank 1 constraint satisfaction, or R1CS for short. Just by a show of hands, how many of you have heard R1CS before? Okay, maybe like a third of you. That's great. Okay, so this is a language that. By the way, just as a warning, today is a technical talk. I'm an optimistic person. I like to try to explain technical things also to general audiences. I don't expect you to follow everything, but I will try to go slow and try to be clear. And if you learn something technical from today's talk, I'll be happy about that, okay? So rank 1 constraint satisfaction is actually a very simple language. Here it is. I'm going to define it for you in a little box. It says, let me give you 3 matrices, ABC, and some public input X. The question, the problem that you're trying to solve is, does there exist a secret input W such that if you take A and you multiply it by the vector XW, and you take B and you multiply it with the vector XW, and you take C and you multiply it with the vector XW, you get 3 vectors that are sort of coordinate-wise multiplications of one another, okay? So notice that the first matrix vector multiplication gives you a vector. The second matrix vector multiplication also gives you a vector. And that circle in the middle means that I am multiplying the 2 vectors coordinate-wise. Okay? And so I want to compare whether the first coordinate of the first vector times the first coordinate of the second vector equals the first coordinate of the last vector, and so on and so forth for all coordinates. Why are we looking at this funny-looking problem? Okay? Well, first and foremost, it generalizes a rather natural type of computation, which are circuit computations. Okay, circuits are maybe not that natural, but they're actually natural for cryptographic proof systems. It is a type of problem for which we can construct proof systems rather easily. Okay? And this problem of rank 1 constraint satisfaction, it is even more general than that. So it is easier to program problems of interest within this type of representation. At the same time, this notion of rank 1 constraint satisfaction is sufficiently simple and has beautiful mathematical structure for which it is easy to build proof systems. So it kind of balances the notion, it balances the 2 needs of programming problems of interest within this sort of a language, and balancing on the other side, building proof systems that are efficient for it, okay? So kind of it's a good trade-off between the front end and the back end. This is not just in principle. In fact, we have plenty of, or maybe not plenty, but we have quite a bit of empirical evidence that real-world programmers out there, they have been able to express problems of interest in the language of R1CS and build products that are sort of running today. For example, Zcash, the core zero-knowledge proof, is about a rank 1 constraints satisfaction is a system of rank 1 constraint satisfaction equations that captures private transfer of money from one address to another. Okay? So targeting this language is sort of empirical interest. Okay? Okay, so that's R1CS. And this morning we saw actually an entire talk that was discussing how do we go about sort of building infrastructure so that we can program and express properties of interest, gadgets, within this language. In this work, we put forward a construction of a ZK snark, okay, that does not have a trusted setup, okay? It only relies on public randomness, cryptographic hash functions, and it lets you prove satisfiability of rank 1 constraint satisfaction problems, okay? And the parameters of this proof system are that it has a good proving time, a good verifying time, and the key aspect here is we get very small proofs, okay? They're exponentially smaller than the computation it attests to. So if n denotes the number of constraints, or you can think about the number of gates in your circuit, that's the size of your computation, the proof size grows only polylogarithmically, okay, in the size of the computation. Does that make sense? So that's the key efficiency property we're trying to achieve here. Now, in terms of real-world numbers, you can think about that the proving time for maybe millions of gates is mere minutes. The size of this proof is going to be on the order of a few tens of kilobytes, just like in the prior talk, okay? And verification is going to amount to a few seconds, okay? Now, why are we studying these type of constructions is because they have this transparent setup, but also because they only make black box use of symmetric key cryptography, just cryptographic hash functions, and therefore these are a class of primitives that are plausibly post-quantum, and we have very, very few constructions of SNARKS that could withstand a future sort of quantum apocalypse. So it is important to study also the class of SNARKS that could potentially survive that. Okay. Now, just for a comparison, how does this sort of new addition to the sort of family of existing constructions of SNARKs compare against constructions we may already be familiar with? Well, first, the proof size that we achieve is 50 times larger than, for example, bulletproofs. It is another proof system for circuits that has a transparent setup. So what we learn is that these proof sizes are not at all competitive with other constructions that rely on public key cryptography that, for example, leverages the hardness of discrete logarithms, okay? So what we learn is, the power of public key cryptography really helps in proof size. On the other hand, what we achieve in this work is that among the class of constructions that only use symmetric key cryptography and is plausibly post-quantum, we achieve a 10x sort of improvement in a proof size compared to prior works that when applied to circuits, okay? So the punchline is that in this work, we achieve the smallest known to date post-quantum SNARK for circuits or rank 1 constraint satisfaction problems, okay? So what I would like to do right now is tell you a little bit about what's happening inside this SNARK, and in fact, more generally, where do this class of post-quantum SNARKs come from, okay? So that's what we're going to do right now. So actually, the first SNARK that was discovered and built inside the cryptography community was already done in the mid-90s. Back then, we didn't call them SNARKs. We had different names. But back then, already in the 90s, we had constructions that basically said that if you give me something called a probabilistically checkable proof, which is a type of proofs that you can write down, you can sort of check them by querying a few locations in the proof only. Then using such a proof, you can build a SNARK. And already back then, this construction had these properties that today we recognize are very attractive, such as a transparent setup, lightweight cryptography. You only use sort of these things called random oracles, which are cryptographic hash functions, and it's plausibly post-quantum secure. Already in the 90s, we had such things. Funny enough, inside the theoretical cryptography community, they were mostly treated as bad constructions because they were making use of strong cryptographic assumptions, namely this random oracle. And so they were, for the most part, not treated, I wouldn't say seriously, but not as satisfactory constructions for the better part of 20 years. But from our perspective of today, from a practical perspective, these are great properties to have in practice. Okay, they're easy to deploy, they're post-quantum, they don't use any heavy cryptography, that's great. So from our perspective of today, why don't we just go ahead and deploy them? Well, the problem is that they rely on really heavy information theoretic components underneath, these things called PCPs, for which we don't have, to this day, even good asymptotic results, and even more so, we don't even have good implementations of these objects. Now, okay, so then it means that whatever I am discussing today is not built out of these objects, okay? So how do we achieve post-quantum SNARKs today? A few years ago, in a paper with Ailey and Nicholas Spooner, we proposed alternative approach, which is to consider an extended notion of PCPs, which we call the interactive oracle proofs. It's some sort of multi-round analog of these probabilistically checkable proofs. And over the past few years, we have been able to show that within this model, we can still achieve all the previous advantages of PCPs while circumventing many of these efficiency barriers. For example, we were able to achieve interactive oracle proofs with optimal proof size. And also, we've been able to put forward concrete efficiency improvements by way of prototypes. So for example, the SNARKs that you heard about in the prior talk, they are precisely built off on a specific choice of interactive oracle proof underneath. There is all of the scalability properties and good efficiency come from advances and implementations of interactive oracle proofs on top of which we later add cryptography. Okay? So this is where today's post-quantum SNARKs come from. And coming back to what we do in this work, if we want to focus on the language of R1CS, then it sounds reasonable. It shouldn't be surprising that the core of the work is designing an interactive oracle proof for this problem. Okay? We want to design an interactive oracle proof for checking satisfiability of this problem of rank 1 constraint satisfaction. So that's exactly what we do in this work. We're able to prove that for this problem, you can achieve optimal sort of proof size. This is the size of the proof that you're probabilistically checking that is linear. Okay? The query complexity to sample out of this proof is logarithmic. You see the exponential gap here. And this query complexity is what ultimately determines the size of the SNARK. Okay? This sort of very small proofs that we can generate. Okay? So that's the main construction of this work. See, people are still not following on the ground. They're still following. Okay? All right. So actually, if I had, this sounds like very arcane, but actually something that I like about this particular work is that the construction behind it is actually not that difficult. If I had, okay, maybe not half an hour like I did today, but if I had a full hour, then I could actually give you a reasonable picture of what's happening inside the protocol itself, and you would have some sense of what's happening. What I will do instead, because I think I have maybe 10 minutes or so, is I will tell you a little bit about just the high-level structure. How do you go about taking a problem like R1CS and checking it with small proofs? So let me jump to that part, which is what I want to do. Tack, 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 and there we go. So this is the problem that we want to check. I give you 3 matrices and a public vector X, and I want to ask whether I can extend this public vector with some secret extension so that A times Z times B times Z equals C times Z, okay? This is like I'm checking that the first coordinate of the first vector times the first coordinate of the second vector equals the first coordinate of the third vector, and so on and so forth for all coordinates, okay? This looks funny, but actually it looks like a circuit, okay? If you think about it, you can sort of easily program circuits inside it. Now, the naive way to check this problem would be to just, for the prover, to send to the verifier this secret Z, okay, that contains W inside it, okay? Now, let's forget about X. Let's assume that sort of this matrix is a square, so we can sort of put aside all these details. The naive way would be to just send Z. Now, this is naive because if I just send you Z, Z is large, is at least as large as the entire computation, so I haven't really saved anything, okay? Okay, let's maybe try to make the problem simpler. Let's try to, instead of thinking R1CS, let's think about various subproblems, each of which is simpler. Maybe we can solve each of these subproblems with a subprotocol, okay, that will let me communicate less information. So what if I were to send you, instead of just Z, also A, B, and C, and then you, as a verifier, you check that A, B, and C are the correct sort of linear transformations of Z, and that A, B, and C, given that they are the correct linear transformations, they satisfy this sort of a coordinate-wise product. Okay? All I've done is that whatever I was checking before, I have translated it into 4 subproblems that are equivalent to what I was checking before. Okay? Before I had AZ times BZ equals CZ. Now I'm just telling you what the results are of those products, and I'm just checking that the linear transformations on their own are fine, and then the product is fine. Okay? I'm just sort of saying that I can break it into subproblems. Now, if I just send you all these vectors, again, it's unclear how you could check these linear relations or product relations by asking just a few queries, so we have to do a little bit more. So maybe this is one slide that I want to try to get across, and I think I'll be, maybe the only really technical slide. In the prior talk, at some point, the word codes was mentioned, okay? So in all of these SNARK constructions, the theory of error correcting codes plays an important role. Why? Because you take all of these computation traces. For example, in the prior talk, you saw this computation trace of check signatures, then check authentication paths, check more signatures, check more authentication paths. That's a computation trace. What do we do with these computation traces? What happens in all of these proof systems, by the way, this includes also SNARKS deployed in Zcash, we take these computation traces and encode them using special codes, okay, that give us some sort of error-correcting properties that later give rise to these properties of probabilistic checking. In these constructions, the code of choice is something called the Reed-Solomon code. This is a foundational and a sort of central code, both in the theory of error-correcting codes and also in the theory of probabilistically checkable proofs. What's happening here is that when you want to encode information, you're going to pick some field that is large enough. Okay, so there it is, a field. And you pick two sets. One is called the interpolation set. Let's call it H. Inside the interpolation set, you lay out your computation trace. Then you also pick an evaluation set. Now, what do you do with these sets? Well, first you think about that I can put a computation trace inside the interpolation set. And then what you do is you interpolate. That's why we're calling it an interpolation set. You interpolate to get what? You get a univariate polynomial that encodes inside it the information about the execution trace. And then you evaluate that polynomial over a much larger set, maybe 10 times that large. Why? Because now this evaluation has information theoretically inside it, the execution trace, the computation trace, but it has it in some sort of redundant form, okay? Because, and this is, I cannot get into too much technicalities, but essentially, two different computation traces, even if they differ at one step, now, in only one step, once you encode them, they will differ in many, many locations, okay? So somehow it amplifies differences between different execution traces. Now, intuitively, this should have something to do with catching errors in computation traces using a small number of queries, because if there are sort of small differences create big differences in encoding, then it might be easier to find errors in the computation trace, and therefore the prover may have a hard time cheating about the correctness of computation. Okay? This is only at a very high level, but this is just to suggest why there is any role for codes to play here. And at a very high level, essentially what happens inside a protocol such as the one that we present in this work is that we translate each of these sub-problems that we have to check into corresponding questions about polynomials. Okay, so instead of talking about vectors and matrices, now we talk about operations on polynomials, okay? This sort of encodings or execution traces on which we can try now to probabilistically check certain properties, okay? So, for example, in the way that our interactive oracle proof in this work works is that we have sub-protocols for doing these linear relations. We call this the lin check. For checking this coordinate-wise product, we call it row check. And then sort of all of this is reduced down to some sort of objects that I cannot really talk about here that are about testing properties of codes, in particular the Reed-Solomon code. And that's sort of the algorithmic core of these SNARKs. Okay, so enough with the technical things. Let me tell you about, from an implementation perspective, what's happening. So we've been developing a library called libiop. IOP here denotes the fact that it enables the construction of post-quantum SNARKs starting from these objects of interactive oracle proofs. It's a toolchain that we hope to put online in the next, hopefully, like a couple of months. What this enables you to do is to obtain constructions of ZK SNARKs that have this transparent setup, lightweight cryptography, post-quantum. And from the perspective of the programmer only has to supply to the library an IOP protocol, and the library will kind of sort of compile automatically this protocol into a SNARK. In fact, more than that, there's other components that I don't really sort of have time to talk about in this particular talk, but we actually automatize much of the construction of a post-quantum SNARK, and we show how to construct not just our protocol, but other protocols in the literature by sort of assembling these Lego pieces that is a small effort for the programmer to achieve different types of post-quantum SNARKs. I want to also take the opportunity to thank an undergraduate at UC Berkeley. His name is Dev Ojha, who has done some amazing development work on this library, who's been really giving us a lot of help on improving and cleaning up this library, for an upcoming open source release. So I think I have no more time. So the punchline is that in this talk, I have discussed a post-quantum SNARK for the language of rank 1 constrained systems. The key property that we achieve in this work is the shortest proof size for circuits. That's the black line over there that grows with log squared in the size of the circuit. And yeah, so I hope that you learned something about post-quantum SNARKs today, and I'll be happy to answer questions.